Welcome to this session on numerical solution of ordinary differential equations. In the previous sessions, we discussed various numerical methods to solve the differential equation of the form dy by dx is equal to f of xy, given that y of x naught is equal to some y naught, namely Picard's method, Taylor series method, Euler's method and Runge-Kutta method. Now, here we shall discuss a new type of method, namely Predictor Corrector method, to solve this type of differential equations. In these methods, we use a pair of formulae to solve the differential equation dy by dx is equal to f of xy, such that y of x naught is equal to y naught. Using the first of these formulae, called predictor formula, we predict, that is, we compute a crude approximation for the value of y, say yp. We denote the crude approximation of y by yp at the required point. Then we use the second formula called the corrector formula to correct or to refine this value of yp and get a better approximation for the value of y, namely yc, yc1. If necessary, this value of yc1 is again substituted in the right hand side of the corrector formula to get a still better approximation of y, namely yc2. This process is repeated until the convergence occurs, that is, two consecutive values of y are almost equal. Usually, the predictor formula and the corrector formula in any combination will have errors of the same order. However, a corrector formula is generally more accurate than a predictor formula, as the coefficient in the error term of the corrector formula is smaller. Many predictor corrector combination formulas are available. First of all, we discuss Euler's predictor corrector formula. Euler's predictor corrector formula uses the symbol Euler's formula as the predictor and the modified Euler's formula as the corrector, though the errors in these formulas are of different order. We shall assume that the values of x, namely x naught, x1, x2, etc., xm, etc., are equally spaced with step size h, so that xm is equal to x naught plus h, which is the step size, x naught plus m into h, and xm plus 1 is equal to xm plus h. Xm plus 1 can be written as xm plus h. Here m varies from 0, 1, 2, 3, etc. The values of y corresponding to these values of x, that is corresponding to x naught, x1, x2, etc., xm, etc., are denoted by y is equal to y naught, y1, y2, etc., ym, etc. The solution of the differential equation dy by dx is equal to f of xy, such that y of x naught is equal to y naught is given by the symbol Euler's formula y of x plus h is equal to y of x plus h into f of xy. This is from the Euler's method. we already discussed in the previous sessions. That is, this can be written as y of x plus h is equal to y of x plus h into f of x y is dy by dx, that is y dash of x. And also by the modified Euler's formula, we already discussed the modified Euler's formula. Y of x plus h is equal to y of x plus h by 2 into y of x plus h by 2 into f of x y plus f of x plus h comma y plus h into f of x y, f of x plus h comma y plus h into f of x y. That is y of x plus h is equal to y of x plus h by 2 into f of x y is y dash of x plus f of x plus h comma y of x plus h. This is y of x plus h, that is y of x plus h into f of x y, that is y of x plus h. Y of x plus h is equal to y of x plus h by 2 into y dash of x plus f of x plus h comma y of x plus h. Therefore, we can write y of x plus h as y of x plus h is equal to y of x plus h by 2 into y dash of x plus this is y dash x plus h, because y dash of x is f of x comma y. We can write f of x plus h comma y of x plus h as y dash of x plus h by using the given differential equation. Now, putting x is equal to xm, and note that xm plus 1 is equal to xm plus h. We are putting x is equal to xm. Here xm plus 1 is equal to xm plus h, ym is equal to y dash of xm, ym. Ym is equal to y of xm. We use this notation ym for y of xm and y dash m for y dash at xm. Therefore, we can write this as y of x plus h is equal to y of x plus h into y dash of x, can be written as y m plus 1 is equal to y m plus h into y dash m. And this expression can be written as y m plus 1 is equal to y m plus h by 2 into y dash m plus y dash m, y dash m plus y dash m plus 1. By using these notations, we can write y of x plus h is equal to y of x plus h into y dash x as y m plus 1 is equal to y m plus h into y dash m, and this expression can be written as y m plus 1 is equal to y m plus h by 2 into y dash m plus y dash m plus 1. This formula can also be derived using the trapezoidal rule of integration as follows. That is, we can derive this formula by the trapezoidal rule of integration. That is, ym plus 1 minus ym can be written as integral from xm to xm plus 1 y dash dx, that is equal to h by 2 into y dash m plus y dash m plus 1. This is from trapezoidal rule of integration, that is, ym plus 1 is equal to h by 2 into y dash m plus y dash m plus 1. Since y dash of x is equal to f of x y, from the given equation we can write y dash xm is equal to y dash of xm is equal to f of xm comma y of xm that is y dash m is equal to f of xm comma y of xm is ym, that is equal to fm. We say this as fm. Using this notation, we can written these two expressions as ym plus 1 is equal to ym plus h into this is fm, y dash m is fm, and this can be, this expression can be written as ym plus 1 is equal to ym plus h by 2 into f of y dash m means fm plus y dash m plus 1 can be written as fm plus 1, that is ym plus 1 is equal to ym plus h by 2 into fm plus fm plus 1. In the predictor formula, the unknown ym plus 1 is expressed in terms of the known value of ym. In this expression, the unknown ym plus 1 is expressed in terms of ym. Ym means the known value of ym, whereas in the corrector formula, the unknown, in this corrector formula, the unknown ym plus 1 is expressed in terms of ym plus 1 itself. This is the characteristic feature of a corrector formula. It is observed that we require only one preceding value of y, namely ym, in order to compute ym plus 1. However, if two preceding values of y, namely ym minus 1 and ym, are known, it will be advantageous to use the predictor formula as ym plus 1 is equal to ym minus 1 plus 2 times h into y dash m. If two preceding values of y, that are ym minus 1 and ym, are known, we can use this expression as the predictor formula to solve this type of differential equation, because the errors in the formulas, in these two formulas, are of the same order. This formula is derived as follows: ym plus 1 is equal to integral from ym plus 1 minus ym minus 1. y m plus 1 minus y m minus 1 is equal to integral from x m minus 1 to x m plus 1 y dash dx. Y dash x may be treated as a constant in the small interval x m minus 1 comma x m plus 1. In this small interval x m minus 1 comma x m plus 1, this y dash x may be treated as a constant of length 2h. Here the length of interval is 2h, because here this is the point x m minus 1 and this is x m plus 1. Therefore, the width of interval is 2h, and hence assumed as y dash m is equal to the value of y dash of x at the midpoint x m of the interval. Therefore, y m plus 1 can be written as y m plus 1 minus y m minus 1 can be written as, this is equal to y dash m into integral from x m minus 1 to x m plus 1 dx, that is equal to 2h into y dash m, 2h into y dash m, that is y m plus 1 minus y m minus 1 is equal to 2h into y dash m. Now, consider an example. Using this method, that is using the Euler's predictor corrector method, find the value of y of 0.1 and y of 0.2, given that dy by dx is equal to y minus 2x divided by y minus 2x divided by y, such that y of 0 is equal to 1. We want to find value of y 0.1 and y 0.2 using the Euler's predictor corrector method for this differential equation. The given differential equation may be written as y dash is equal to y minus 2x divided by y. Here y of 0 equal to 1 means that x naught is equal to 0. That is, we take x naught is equal to 0, y naught is equal to 1. Therefore, y naught dash is equal to y dash, the given differential equation is y dash is equal to y minus 2x divided by y. Therefore, we can write y naught dash, that is the derivative at x naught y naught, that is y naught dash is equal to y naught minus 2x naught divided by y naught. This is equal to y naught is 1 minus x naught is 0, therefore, this term will become 0, that is y naught dash is equal to 1. Here we take h as 0.1, because we are given y of 0 equal to 1, that means x naught is equal to 0. We want to find y of 0.1 and y of 0.2. We take h as 0.1. x1 is equal to 0.1. We take this value as x1, and y1 is equal to y of x1. We denote y of x1 as y1. By Euler's predictor formula, we write ym plus 1 is equal to, this is our predictor formula, Euler's predictor formula, ym plus 1 is equal to ym plus h into y dash m. Putting m is equal to 0, we get y1 as y naught plus h into y naught dash. Therefore, the first initial approximation y10 is equal to 1 plus here y naught is 1, h is 0.1 into y naught dash is 1. This is equal to 1 plus 0.1, that is 1.1. Now, y1 dash 0 is equal to y1 0 minus 2x1 divided by y1 0, which is equal to, here y1 0 is 1.1 minus 2 into x1 is 0.1 divided by y1 0, that is 1.1. This is equal to 1.1 minus 0.2 divided by 1.1, which is equal to 0.91818. On simplification, we will get y1 dash 0 as 0.91818. Now, the Euler's corrector formula is ym plus 1. We use I for the iterations, which is equal to ym plus h by 2 into y dash m plus y dash m plus 1, y dash m plus 1 I minus 1. In this, we substitute m is equal to 0, we get y 1 and we substitute m equal to 0 and I is equal to 1. In this expression, we will get y1 1 as this equal to y of 0 plus y0 plus h by 2 into y dash m, that is y dash 0 plus y dash m plus 1, that is y dash 1 0. 0 means the initial approximation. This is equal to y naught plus h is 0.1 divided by 2, that means 0.05 into y naught dash is 1 plus y1 dash 0, that is 0.91818, which is equal to, on simplification we will get this as 1.09591. Now, y1 dash 1, which is equal to y1 1 minus 2x1 divided by y1 1, which is equal to 0.91341. By substituting all these values, we will get, on simplification, y1 dash 1 as 0.91341. Now, taking I is equal to 2 in this expression, we will get y1 2 which is equal to 1.05 plus 0.05 into 0.91341. On simplification, we will get y1 2 as 1.09567. Now, y1 dash 2 which is equal to y1 2 minus 2x1 divided by y1 2 which is equal to 0.91313. Now, taking I is equal to 3, this is for I is equal to 2. Now, we take I is equal to 3, we will get y1 3 as, from this expression we will get y1 3 as 1.05 plus 0.05 into 0.91313. On simplification, this is equal to 1.09566. And y1 dash 3 which is equal to y1 3 minus 2x1 divided by y1 3 which is equal to 0.91312. Taking I is equal to 4, we will get when I is equal to 4, we will get y1 4 as 1.05 plus 0.05 into 0.91312. On simplification, this is equal to 1.09566. Here y1 4 is equal to 1.09566, and in the previous step we obtained y1 3 as 1.09566. These two are same, therefore, the convergence has occurred, and hence we take the value of y1 as y1 is equal to y1 means the value of y at 0 x is equal to 0.1, which is equal to 1.0957 approximately. Now, we take x1 is equal to 0.1, x1 is equal to 0.1, y1 is equal to 1.0957. We will obtain y1 dash is equal to y1 minus 2x1 divided by y1, which is equal to 0.91317. Here h is equal to 0.1 and we take x2 as 0.2. This is x2. x2 is equal to 0.2 and y2 is equal to y of 0.2. Using the Euler's predictor formula, we can write ym plus 1 as ym plus 1 is equal to ym minus 1 plus 2h into ym dash y dash m. that means y2 is equal to, for m is equal to 1, we can write y2 is equal to y0 plus 2h into y1 dash. Therefore, y20 is equal to 1 plus 0.2 into 0.91317, which is equal to 1.18263. This is y20. y2 dash 0 is equal to y20 minus 2x2 divided by y20, which is equal to, by substituting these values and simplifying, we will get 0.84440. Now, taking m is equal to 1 and I is equal to 1, we have y21 is equal to y1 plus h by 2 into y1 dash plus h by 2 into y2 dash 0, which is equal to 1.0957 plus 0.05 into 0.91317 plus 0.05 into 0.84440. On simplification, we will get this as 1.18358. Similarly, we can compute y2 dash 2 as 0.84582. y22 is equal to 1.18364 and y2 dash 2 is equal to 0.84570. y23 is equal to 1.18365. y2 dash 3 is equal to 0.84571 and y24 is equal to 1.18365. Here we obtained y23 as 1.18365. Therefore, the convergence attained, and hence we take the value of y2, that is y2 means y of 0.2 as 1.1837 approximately. Now, let me conclude this session. In this session, we discussed the Euler's predictor corrector formula to solve the ordinary differential equation of the form dy by d is equal to f of x y, given that y of x naught is equal to y naught. Thank you for watching this class. Have a nice day.